Anybody? Come on, people. There are 55 people in this meeting, not one person. Hello. We need someone to do minutes. I'd like to get started. You're going to hear my lovely voice until we get somebody to do minutes. Wes, thank you. And Brian, thank you. I think if Brian, you guys can sort it out, but presumably Wes can do it. But between you two, I'm very grateful. Thank you so much for doing that. Well, welcome to ICCRG. We're meeting after 6 months, and it's been a while. So we've had a large number of people having things that we unfortunately we did not have enough time to present here. But I want to start off this meeting by, before I do the agenda bash, just very quickly note a couple of things. First, the note well, as you all know, applies. The important thing I wanted to point out here is that I would like to really try and shift the focus away from presentations at meetings to discussions. I'm probably going to slowly start insisting that those who want a presentation slot actually have initiate a discussion on the list first, so that it doesn't seem like a one-shot thing. I mean, we've always had this problem with ICCRG, I think, where people come do a presentation, walk away, and it's 10 minutes of engagement for 3 months, which is not particularly exciting or interesting, and there's no continuity. So I want to encourage everybody to participate on the list. I want people to bring topics up on the list, and if the topics are interesting, I would like to give that time on the agenda. And I will say that topics that are getting discussion on the list will have priority when it comes to agenda time at a meeting. So keep that in mind, and I'll move along. One more thing before I get onto the agenda is that later today, during the IETF Open, there's a talk by Renisha Ware of CMU. She will be presenting on, I don't remember the name of the talk, but it's about the Jane Fairness Index and moving past the Jane Fairness Index to measure fairness amongst flows. And it's a very interesting piece of work. I encourage you to show up and give feedback. I'm sure you will be interested in this talk. With that, let's get started. We have a packed agenda today, so we're going to try and keep this on time. We have Praveen doing an update on Ledbat. And then we have a special guest, Ayush Mishra, who will be talking about a really interesting paper where they've done some fascinating work on measuring TCP congestion control deployment on the internet. We have Neil from Google giving us an update on BBR v2, followed by Sylvester, who will be talking, I think, about BBR unfairness, and then Bob talking about TCP Prague congestion control. And if we have time, we will have a chance to talk about MPDCCP as well. So it's a packed agenda. Let's keep this to the speakers. Let's keep this within time. I'm going to try and move you along if I need to, and I would like to get started. So I'm going to take, I think, charge of the slides here, and I'll run them. I know, Sylvester, you were going to try and do your own slides, and that's fine. But I will. I'm going to cue Praveen now. I'm going to switch this to my to your slides. Praveen.
All right. Can you see and hear me?
Can see you. Hearing is. You might want to move your mic down.
Better now?
Slightly better. Can you go a little bit? Oh, I'm sorry. It's me, not you. Hang on.
Waiting for the slides to show up. Okay. Hello, everyone. Everybody is probably in different time zone. After a long time, we have ICCRG, so happy to see everybody here. Today, I'm going to talk about our Ledbat. We have an update on our Ledbat. This is joint work with others at Microsoft, and also Marcela and Alberto from UC3M. I missed Gabriel's name. Sorry about that. Jana, can you move to the next slide, please? So what is our Ledbat? A quick recap. So what we want to do is we want to bring the benefit of Ledbat++ to the receive side of the transport connection. For those who don't know what Ledbat++ is, it's an improvement over the original Ledbat RFC to solve a bunch of shortcomings of that RFC. So Ledbat++ is a sender-side congestion control algorithm. What we want to do is bring the same benefits of that algorithm to the receive side of the transport connection. How we do this? We use the flow control mechanism. So as you know, each TCP packet contains the window field, which advertises to the peer how much data it can buffer. And that is typically a typical TCP implementation would tune that buffer over time to make the performance good. So we would increase the window as long as the sender is able to keep up and the application is draining data. But in this case, what we want to do is use that as a throttle. So based on the Ledbat algorithm, we want to actually control how much data the sender is able to send, effectively implementing a less than best effort congestion control for the end-to-end connection on the receive side. One of the key points there is, yeah, we don't want to shrink the advertised window, but based on the computed window, we can over time reduce it over the period of RTT. Why do we want to do this? Why is it important to do this on the receive side? Three major reasons. One of the challenges is that a lot of like software updates, which is one of the primary use cases for background transfers, uses CDNs, and having control over those servers is difficult. Most of them don't have Ledbat++ support. The second reason we want to do this on the receiver is that there can be proxies on the path. Corporate networks have a lot of proxies. And that can prevent the sort of less than best effort happening end to end. The network on the client side might be overloaded, and just doing it in one path of the network is not sufficient. And of course, there's like cases where the receiver application has more information about exactly which connections need to be lower priority and might not be able to communicate that to the server side. And doing this just using the client side application has a lot of advantages, including having enforcing any sort of preference that the local application or operating system that wants to apply less than best effort. This is based on the draft that is co-authored by everybody that was on the first slide. Please, next slide, please, Jana. So the update I have is that we have an implementation now in the Windows operating system. This is based on the draft. It's implemented for TCP. We already had an API and sort of configuration in the OS to turn on Ledbat++. The same one also enables our Ledbat. So when you enable this, you get less than best effort in both send and receive directions. It includes all the additional mechanisms of Ledbat++. The rledbat draft leaves it open to the implementation, at least the current version of the draft leaves it open to the implementation to either use Ledbat or Ledbat++. We have chosen to implement all of the goodness of Ledbat++, which includes RTT measurement, slower than Reno increase for the window with the adaptive gain factor. We also do the multiplicative decrease to solve inter-Ledbat fairness and latecomer advantage problems. We also have a modified version of slow start, which exits early based on delay increase. And we have the initial and periodic slowdown, which helps us measure the base delay accurately throughout the lifetime of the connection and solve the latency drift problem. One of the key things here is that when you turn this on, we automatically negotiate TCP timestamps. If TCP timestamp negotiation fails, effectively the algorithm is disabled. At that point, it becomes, it generally just falls back to a traditional TCP connection. We do expose that information after the application, so the application could apply like a static throttle for these kind of workloads. Next slide, please. So what are the there are some deviations from the draft that I wanted to call out. The periodic slowdown algorithm in Ledbat++ is complicated. For this our Ledbat implementation, we have chosen to make it more simplified. So instead of targeting only a 90% reduction, we are basically doing one slowdown per each measurement interval, and that measurement interval is also different than the one for Ledbat++, which was 30 seconds. This is like 60 seconds period for measuring the base delay. It's basically a periodic slowdown. We also have a different target delay. This was arrived at based on some measurements. The target delay of 60 milliseconds was used in Ledbat++, but we found that on the receiver side, we had to use a lower value. We're still sort of experimenting and tuning these constants. And once we have more results with the real world workload, we will update the draft with the correct recommendations. Next slide, please. So I have some initial lab results. I don't have data from like a wide deployment yet, but this is just to show the effectiveness of the algorithm as implemented on the receive side. So this is just a cubic short flow that kicks in during the middle of a R-Ledbat connection. As you can see, the connection lamps up, the sender doing slow start. Then we basically enter the slowdown period. That's the initial slowdown, and we throttle the sender completely. This is what would have happened if the sender was using Ledbat++, but in this case, it's the receiver throttling the sender. And then we exit the slowdown. We continue our growth, but then the cubic flow kicks in and the reaction is pretty immediate. We can sense the delay build up in the bottleneck, and we back off to the minimum rate, which is the 2-packet window that is recommended by Ledbat++. And then once the cubic flow leaves, as you can see, the ramp up is pretty slow here. There is a 50 millisecond RTT, and because we are still slower than Reno, the growth is pretty slow. Next slide, please. This demonstrates the latecomer. This basically shows that the latecomer advantage problem does not exist with our Ledbat. So what happens here is that when the latecomer flow starts, the slowdown, the periodic slowdown, basically allows the flows to remeasure the base delay, and that causes both the flows to sort of fair share, and we don't see that the latecomer gets an undue advantage and completely throttles the first flow. This is the same configuration with a 50 millisecond 100 Mbps link. Next slide, please. This sort of shows the inter-Ledbat fairness for R-Ledbat flows. These are 4 different R-Ledbat flows, staggered started. As you can see, there's periodic slowdowns happening for all of these flows. As a result, they all measure the base delay accurately, and they're able to fair share the link amongst themselves. This does not show what would happen if you put in a cubic flow, but as soon as you have a cubic flow, all of these would back off and then ramp back up when there's no competing traffic. Next slide, please. This is the low latency competition. Effectively, this is the problem where the queue is small enough. Actually, there's a mistake on the slide. The queue size was actually 250 packets. So this is actually a shallow queue. And because we can't build the queue, we can't exceed the target delay, so Ledbat would not back off. We had the same experiment with Ledbat++, and when it was a sender, and we would see that it was actually taking much smaller share compared to Cubic. But with our Ledbat, we are seeing that there is actually a little bit more competition. It's almost as if they're fair sharing. But this is a problem we will continue to investigate. We haven't root cause this yet, but this is something that needs to be investigated. So certainly different behavior than what we saw with Ledbat++ on the sender side. Next slide, please. That's sort of the summary of where we are at. The next step for us is to take this implementation out for a spin with a real-world software update workload and measure its effectiveness. Measuring this is hard. Less than best effort in general. Metrics for this are really hard problem, particularly because the goal is to actually improve other traffic. We have had cases where people had to drop off the call and go tell their family members to stop doing things on the network. So it's basically a user experience measurement. We have ways of doing this, so we're still working on creative ways to measure the effectiveness of this algorithm in the real world. We want to do constant tuning. There's a bunch of magic constants. I think this applies to both Ledbat plus and RLedbat. The other thing we want to explore is the making the target value dynamic. Currently, it's 60 milliseconds for Ledbat plus and 40 milliseconds for RLedbat. We would like to figure out a way to tune this based on the bottleneck link. One of the challenges here is that because it's a less than best effort algorithm, we can't really send at a very high rate to figure out the capacity of the link. So this is a challenging problem. We're still figuring out how best to do this. There is a problem with BBR-v2. So we took the latest alpha release of the Linux implementation of BBR-v2 and took it for a spin with Ledbat++ in the lab. So the same thing should apply to our Ledbat as well. Effectively, they're the same algorithm implemented on either side. So the problem here is that we don't really see a queue build-up with BBR, which is kind of by design. And as a result, we sort of enter the low latency competition mode, and our Ledbat and Ledbat++ are not backing off. So we have to do more work here to figure out how best to do less than best effort in the presence of an algorithm like BBR-v2. So this is interesting avenue for research. If there are folks on this group who want to contribute here, we would be very happy to hear about any ideas. On the draft side, we have both drafts currently adopted in ICCRG. On the RLedbat side, we may want to think about just referencing Ledbat++. I don't really see the point of going back to Ledbat with the known problems. We also want to update the draft based on the data and the tuning. On the Ledbat++ side, we want to add pseudocode. That's been an ask from a lot of people so that the RFC draft is easier to read and implement. And there has been a suggestion to also make it standalone instead of having to refer the original Ledbat RFC and sort of replace the original one. And that there's a third point I miss here, which is to also make it agnostic to transport. Right now, both of these drafts are very much specific to TCP, whereas they could also be applied to QUIC. So that's the third sort of work that needs to happen for these drafts. With that, I think I'm done with my talk, and I'll be happy to take questions.
Thanks for
that, Praveen. Ian, you're up.
Thank you. Thank you for this. Certainly an interesting idea. I have to ask a question though, like if you had your way, would you prefer a server-side only approach? Because assuming all servers implemented something that was of the shape of Ledbat plus, and we can agree on the HTTP priorities draft that like the lowest priority actually like indicated a congestion control change, and maybe we can get like similar results. Just an idea. It's kind of cross-layer, but given I'm like very aware of both drafts, it's worth thinking about. But everything else sounds interesting, and thanks for continuing this work.
If you look at the original problem, right? So you could do this on the server side, which is how we started out with as a congestion controller. The challenge is proxies. The challenge is not in not all applications we can modify to inform the sender about which connection is lower priority. So there's some challenges doing just on the server side. One of the good parts of our Ledbat is that it can easily coexist with the Ledbat plus on the sender. So there's no like interop problem here. So let's say the server decided to do Ledbat plus and the same time client is doing our Ledbat. Those would just coexist very peacefully. And one of the advantages of our Ledbat is that you don't need any changes on the sender side. But yeah, I think like both have their advantages.
Yeah, messing with flow control always makes me a little bit scared, but I agree that it does work.
For Quick as well, because Quick has flow control as well.
Yeah, I'm going to inject myself at the end of the line and also close the queue here. Yucheng, you're next.
Thank you for this talk. Why does it critically depend on TCP timestamps? I saw that you disable Ledbat if timestamp is not negotiated.
Yeah, good question. I think this is covered in the draft. So basically, we want to be able to take RTT measurements, and that's the basis of the algorithm, right? We use latency measurements. The challenge is that if you're a pure receiver and not sending data throughout the life of the connection, you cannot accurately measure RTT. So that's the reason we have a strong dependency on the timestamp option.
I see. Thank you.
Vidhi, you're next.
Can you hear me?
Yes, we can now.
Yes, we can now. Thank you. So I have a lot of questions because I have been actively looking into this. I did send some emails to the mailing list for the things that I have found. Couple things that I have yet not updated on the mailing list. One thing is when you do inter-Ledbat experiment, don't you sometimes see a delayed ACK problem in the RTT estimate? Because that's what I was seeing, and some of the flows were really like struggling to get any bandwidth at all.
This is actually covered in the draft. So
in the
sorry, I'm hearing my own. This is covered in the draft. So we apply basically a min filter.
Vidhi, there's a lot of echo coming. There's echo coming from your side.
I'm gonna mute myself.
Thank you. Go on, Praveen.
So we have a window filter that we apply to all these RTT samples, which allows us to sort of weed out the delayed ACK samples. One of the things I would point out is that the workloads we are looking at are mostly continuously transferring data. Because these are like update workloads which always have data to send even if it is in chunks. So applying the window filter for the most recent and received RTT samples is really important. That will allow you to sort of overcome the delayed ACK inflating the RTT problem.
Send or receive Ledbat.
I didn't catch that. Was that a question?
Did you do you do that for both the receive Ledbat and Ledbat plus plus?
Yes, we do it for both, and it's more important on the our Ledbat side because if you're not sending data, then you're completely dependent on using the timestamp technique to measure RTT. But yeah, if you're sending data, then the delay lag problem can come.
Second question was the dynamic target.
Vidhi, I'm going to have to interrupt you. We have a number of people in the queue. Would you be able to take this to the list?
That's okay. But I just want to ask one last question, which is a little bit more important. Was the base delay is, I think the base delay interval is 10 minutes in the Ledbat plus draft, not 60 seconds, which I noticed in the slides, right?
I'm pretty sure it's 60 seconds for Ledbat plus plus. Maybe there's a problem with the draft. But let's take this offline. I'll be happy to answer on the mailing list.
Okay, cool.
And I have your other emails as well asking questions. So I'll respond to all of them later. Yeah, thank you.
All right. Let's keep this quick, folks. We are going past time now. Jeff, you're up.
I gathered from slide 8 that it seems like you're assuming some kind of delay bandwidth product queue size in the network, and it doesn't work well on small queues. Let me ask you explicitly, what assumptions is Ledbat making about the network queue sizes? And in relation to this sort of recent work about trying to reduce the amount of buffering in the network, how does Ledbat react to consistently under-provisioned network buffers when the initial provisioning might have been delay bandwidth product?
Of shallow buffers was attempted to be solved in Ledbat++, which was more effective. So basically, what we do is we are effectively slower than Reno. So there's no assumptions here about what the buffer size is. There are cases where it's BDP or higher, in which case, there is enough buffer for us to build a queue and be able to detect that the target delay has been exceeded. But there is no other assumptions here. But if it's a shallow buffer, the way we solved that problem in Ledbat++ was that our window growth was slower than Reno. So that would basically make it go much slower than competing traffic. That's the best solution we could come up with. As I explained earlier, detecting exactly what the bottleneck capacity is a hard problem for a less than best effort congestion control. So all of these are good areas for research. I also think that as I mentioned, the target value that we have is fixed right now. Making it dynamic is also an important problem that should be solved.
Thanks. That answers my question. Thank you.
Eric, you're up.
Very quickly say thank you, and I'm really interested to see some of the further results and things. We've noticed similar issues in terms of many of the flows that you would really like to be background flows are not flows where you're doing a lot of the sending, and especially around intermediaries, you may not be able to go find all the corners of the internet. So that I think has a real practical use in a way that a lot of the other things we do are helpful in some cases, but not quite as critical. The one thing that would be interesting to know if you've seen is we've discovered a couple of senders, and I can go look up what congestion control they're using, where after you've closed the window down, they take many tens of seconds, if not minutes, to respond to the window opening back up. And I'd be curious to know if either you've seen anything like that, and is that one of those cases where we say, well, it's fine because you're trying to be background flow anyway, and so if it's going to take you, 2.5 minutes before you get back up to actually transferring real data, that's fine because it's in the background, or is that going to be a problem with this kind of a strategy?
That's an interesting problem. So we haven't done at-scale measurements, so I can't tell you if we have seen that problem. That's sort of work that's upcoming. Very happy to keep an eye out for that. So thanks for the heads up. If that becomes a problem, yeah, I mean, we don't want to go artificially slow either. I mean, yes, we are trying to do these things in the background, but if there is enough capacity, we want to be able to saturate it. One of the other problems with going slower than Reno has been that, if you're really on a big WAN link and you artificially slow down, it takes a long time to come back up. So yes, that is also an avenue for more improvements possibly. But I'll keep an eye out and keep you posted. Hopefully another update in one of the other upcoming ICCRGs. So thank you.
Thank you.
I want to take a quick moment to thank Praveen for this. There's clearly a lot of interest in this work, and I think it's the results are super interesting. I have questions about them as well, but I'm going to hold them off for the list, which is the plug I want to make here. Please take these questions to the list. I think that we want to see continued engagement on the list. Praveen's already said that he's interested. They're interested in getting feedback on how to make things better here. Please take those to the list. Make suggestions, engage in conversation there. I'd love to see more of this happen on the list instead of just during the Q&A session here at the ICCRG meeting. I want to, outside of that, just one comment I want to make, which is that people are talking about doing this per stream in QUIC or in HTTP, and that is very tricky. You don't want to do multiple congestion controllers within a single connection. That walks into very, very strange territory. I'll just make that comment and move on. We can have more discussion on the list or on the chat here. Thank you, Praveen. Ayush, you're up next. Let me bring up your slides.
Okay. Can you guys hear me?
Yes, we can.
Okay, great.
I will just go on, Ayush. Why don't you introduce yourself and take it away? Ayush, by the way, for everybody here, is an ICCRG newcomer. So please treat him kindly and make him feel welcomed and happy to be here. Take it away, Ayush.
Okay. Thanks for the introduction, Jana. So hello, everyone. I'm Ayush. I'm a second-year PhD student at NUS. And today I'll be talking about the Great Internet TCP Congestion Control Census. So this was basically a measurement study that we conducted in mid-2019 to figure out who's running what congestion control algorithms on the internet. Next slide, please. Okay. So 30 years of congestion control research have produced numerous congestion control algorithms. And as a result, for most of the internet's lifetime, we have seen a heterogeneous mix of congestion control algorithms. And I mean, I'm just not saying this, but this has also been verified by previous similar studies as marked in brown on the timeline on the slide. But what's happened since the last such study in 2011 is that we've had a new kid on the block. So BBR, which was proposed in 2016, may arguably be the most momentous development in the congestion control landscape yet. And the main reason we feel this way is because for the first time in the internet's history, you're going to have a significant part of internet traffic that's not going to back off when it sees a random packet loss. So what this essentially does is that it introduces an entirely different congestion control mechanic into the existing mix of window-based and loss-based congestion control on the internet. Next slide, please. So with this in mind, what we wanted to do was we wanted to uncover the exact extent of BBR's deployment on the internet and maybe refresh our view of what the current internet congestion control landscape looks like. So to do this, we set out to do a congestion control census of sorts to measure the 20,000 most popular websites on the internet and figure out what congestion control algorithm they run. Next slide, please. So unsurprisingly, it turns out this is a non-trivial task for a variety of reasons. Firstly, while making such a measurement, we will need to isolate the internet's network dynamics so that whatever we see on the receiver end, we can make sure that that's a function of what the congestion controller is doing and not just what the network looks like at that point of time. Second, we would also want to extract a common feature from a variety of congestion control algorithms. Since we don't know upfront what the remote congestion control algorithm is. And finally, we would need to identify these congestion control algorithms within short HTTP page downloads. So this was a design decision that we took very early into this measurement study. And the reason was that most of the websites that we were aiming to measure serve HTTP pages. So it would be the best candidate for conducting such measurements. So our solution to do this measurement study was a tool called Gordon. And Gordon deals with each of these concerns through a variety of strategies and design decisions. Next slide, please. So the first issue, which is isolating the network's dynamics, is dealt by Gordon by localizing the connection bottleneck. So Gordon does this by rate limiting the connection right before the client. And the reason we do this is because this provides us an opportunity to directly control the bandwidth that the sender sees, and it also minimizes the risk of random packet losses on the internet that can potentially be hard to account for when we are doing our measurement. Next slide, please. The second issue, which was selecting a common feature to extract from all our congestion control algorithms, we dealt with this by actually choosing the C-event of the remote congestion controller as the common feature in our measurement. And the reason we did this was because since, whether your congestion control algorithm is window-based or rate-based, it's always going to have a cap on how many packets it can have in flight. And this can essentially become its effective C-event, and this is something that we can measure. So how we measure the C-event is actually through a very simple iterative procedure. So we note that the C-event is the maximum number of unacknowledged packets a sender allows you to have during a connection. So to basically get this number, what we do is we start the connection with a remote server, and then we drop all the packets till we see a retransmit. So in this case, all the packets that we receive before we see a retransmit is going to be the value of the first congestion window, or C1. Next, we start a new connection after some time, and this time we accept C1 number of packets before we start dropping packets again, till we see a retransmit. And in this case, the new number of packets that we dropped will become C2, or the second congestion window. So we perform this procedure iteratively till we exhaust all the data in our target web page, and thereby we produce a C-event evolution graph. We have found that this C-event evolution graph is not only effective enough to differ between the known congestion control variants, but it's also quite handy in making useful observations about any unknown congestion control variants that Gordon might encounter. Next slide, please. The last issue that we had to deal with was dealing with short HTTP page downloads. So how we can deal with this is really simple. We can either look for larger pages, which is exactly what we did. We crawled the target domains for the largest pages we could find. And since our measurements are made on a packet basis, we use the smallest MTU that was allowed by the network path during the connection. So this basically allowed us to extract as many packets as we could from a given page size. Next slide, please. So while making these measurements, Gordon actually simulates two key network stimuli in a way to elicit characteristic responses from a remote congestion controller. And we can encompass these stimuli in something what we call a network profile. And this network profile will be applied to each measurement that Gordon makes. So in this network profile, what Gordon does is it emulates a packet drop the first time the C-event exceeds 80 packets, and it emulates a bandwidth change after receiving 1500 packets. And it does these changes while emulating an RTT of 100 ms. The exact details for why we use these numbers and why we choose these two network stimuli can be found in the paper. Next slide, please. So this is a really interesting slide, and what it essentially illustrates are the distinct congestion window responses for different congestion control algorithms when we apply our network profile. So as we can see, all these graphs have reasonably distinct shapes. And in fact, our classifier uses a decision tree-based classifier that uses these distinct shapes to identify different congestion control algorithms. Again, how this classifier exactly works, you can find more details about that in the paper. Next slide, please. So now I'll cover the measurement results for our measurement study. And let's start with accuracy. Next slide, please. So to measure the accuracy of Gordon, what we did was we set up control servers in various locations on the internet, and we measured them via a local server in the lab. And later on, we reversed this configuration with our local server acting as a control server, and we made Gordon run in various machines around the globe. And what we've seen is that our shape-based, decision tree-based classifier works reasonably well to identify a bulk of the algorithms. And any misidentifications that we see are basically between algorithms that have very similar congestion window evolution shapes, which is something that we expected. But even given that, we can see that for most of our identifications, the accuracy is more than 90%. Next slide, please. So the measurements of the websites themselves were made from servers in Singapore, Mumbai, Paris, Sao Paulo, and Ohio. And for the websites, given our network profile, we found that 16% of the pages were less than the optimal page size of 165 KB. So basically, based on our network profile, we calculated, in the worst case scenario, what is the minimum page size that we need to get a reasonably long C-event graph that we can identify. So it turned out this number was 165 KB, but 16% of the pages we measured were lower than this number. So in case they were lower than this number, what we did was we did a classification on our best effort basis, which is that if we could make identification, we went ahead with it, but if we couldn't, then it was just classified as a short flow. We also found out that about 1,300 websites among the top 20K Alexa websites were unresponsive to our rather aggressive measurement methodology. So I'm going to be referring to these websites as unresponsive websites for the rest of the presentation. Next slide, please. So in terms of the distribution of the congestion control algorithms, in terms of website count, what we found is that Cubic is still the most dominant congestion control algorithm on the internet. And we measured it being deployed by 30.7% of the measured websites. However, it looks like BBR has been adopted at an unprecedented rate since its introduction in 2016. And it's now accounting for almost 18% of the top 20,000 Alexa websites. We also identified a slightly modified version of BBR being deployed by 167 Google-owned domains. And we will be referring to this slightly different variant as BBRG. The other significant shares in the congestion control landscape belong to congestion control algorithms like CTCP, Illinois, Vegas, HTCP, and yet another high-speed TCP. There was also a significantly large chunk of websites that Gordon was not able to classify or classified as unknown. So we'll have a closer look at these websites later on in the presentation. Next slide, please. So given our numbers from the distribution based on just the website counts themselves, I don't think that really gives us the complete picture because not all websites are made equal. And it's likely that more popular websites are contributing more traffic to the internet. So for this, what we did was we just looked at the top 250 Alexa websites. And when we do that, it looks like BBR overtakes Cubic as the most dominant algorithm in the websites that matter. We also noticed that a significant number of the websites that deployed BBR served video content. However, I should note here that it's not necessary for these websites to be deploying DBR for delivering video as well, since our measurements were made on static HTTP web pages. But that said, even if you just consider the static HTTP web pages, DBR is still contributing significantly to the downstream traffic share. Another thing I would like to note, circling back to there being a difference between the video congestion control algorithm and the HTTP web page congestion control algorithm, Gordon actually identified Netflix.com to be using Cubic to serve its web pages. But when we actually reached out to Netflix, it turns out they actually used New Reno to deliver video. Next slide, please. So coming back to the unclassified variants, we found a significant number of websites that Gordon was not able to identify. So to investigate further, what we did was we reran experiments on these websites and introduced a variety of different network profiles to see how differently they react. So in the measured websites, about 14% of them were either short flows that we discussed earlier or did not respond to our measurement methodology. But of the remaining websites that did actually respond and give us long enough C-bin graphs, we found that most of them react to packet losses, but a significant number of them do not react to packet losses. We were also able to identify a variant run by websites that were hosted by Akamai, and I'll be calling this variant Akamai CC for the rest of the presentation. Next slide, please. So Akamai CC on its own turned out to be quite an interesting congestion control variant. From its reaction to various network profiles, what we found was that it did not react to packet loss, but it closely followed whatever BDP was emulated by Gordon. We feel that it's likely that this is a variant of fast TCP. There were some other interesting C-bin evolution graphs that we found as well. So for example, on your right, you can see Amazon.com, which ran a variant that did not really respond to our emulated packet loss and showed HTTP-like behavior in the congestion avoidance phase. Yahoo.co.jp was quite conservative and seemed to exit slow start even before it saw packet loss or saturated the BDP. And on the other hand, Zero.com was on the exact end of the spectrum, other end of the spectrum, which is to say that it did not respond to packet losses or changes in bandwidth. It just seemed to keep 200 packets in flight all the time. Next slide, please. So in summary, what I think we are seeing is essentially a paradigm shift in the internet congestion control landscape. So similar to the transition that we have seen earlier on between AIMD and MIMD, a sizable chunk of the internet traffic today is being controlled by rate-based algorithms like BBR. And we feel this really further underlines the importance of understanding the interactions between these two different schools of doing congestion control and mitigating any unfairness and coexisting issues. Next slide, please. So given that we are seeing such a fast-paced changes in the internet congestion control landscape, we would want to make some changes to Gordon to keep up with these changes. So primary among these is identifying newer congestion control algorithms. So for example, since BBR, we have seen proposals for variants like COPA and TCP Vivace, which are also rate-based. And ideally, we would like to identify them as well. So since the measurement study, we have extended Gordon to measure the receive rate along with the C-wind. And it turns out receive rate is quite handy to differentiate between, not just differentiate, but identify COPA and TCP Vivace in controlled experiments. Lastly, we would also want Gordon to emulate a larger variety of network stimuli. So for example, there might be slightly modified versions of Cubic or Reno that don't respond to one packet loss, but 2 or 3 packet losses that we are not able to emulate, and therefore we're not able to identify them. And we would also want Gordon to identify sub-RTT behaviors, since right now we are constrained to measuring just a per RTT event. Next slide, please. So I would like to end this talk with 2 high-level research questions that our research group has been dealing with since our measurement study. So the first is really understanding how PBR and QBIC will cope with this evolving congestion control landscape. While there has been plenty of work that indicates PBR can be unfair to QBIC in some scenarios, this congestion control evolution is unlikely to be a walk in the park for PBR either. So we have done a lot of interesting work in this front, and I will not go into the details of it in the interest of time, but allow me to illustrate one of our key results through a very simple experiment. So we ran multiple instances of 10 flow experiments with different shares of them running PBR and QBIC. So the first trial, we had only 1 PBR and 9 QBIC flows. The second trial, we introduced PBR to 2, and we kept on doing this till all our flows were PBR. And the graph on the right plots all the BBR flows per flow average throughput as compared to the fair share in that scenario, which is indicated by the dotted line. So what we see is that as you slowly increase the number of PBR flows at the bottleneck, the per flow average throughput of PBR drops very sharply. In fact, at one point, it even goes below the fair share for that bottleneck. So the main point that I'm trying to drive from this graph is that if PBR is working really well today, does not mean PBR will be the obvious choice against QBIC tomorrow. Both for PBR and QBIC, the performance is likely to be a function of what the congestion control landscape looks like. Next slide, please. The second research question we're trying to look at is understanding the rate-based congestion control mechanic. So BPR and other new internet congestion control algorithms that have been proposed since have been predominantly rate-based. Examples of this would be COPA and PCC Vivace. And it's quite common for these algorithms to work on tight send rate and receive rate feedback loops to basically infer what's going on at the bottleneck. We feel that this is a new congestion control mechanic that's still not completely understood. And what we essentially need to do is we need to re-answer some of the key congestion control questions, like on convergence and fairness, albeit in the rate-based setting. So in this direction, we are working on modeling such send rate and receive rate based feedback loops and trying to understand how they work. Next slide, please. Yes, and that's all I have for you today. Thank you for your time, and I'll be happy to take any questions.
All right, we have time for very quick few questions. If you could try to keep this brief, that would be very much appreciated. But thank you so much, Ayush. This is excellent work, and I'm really glad to finally see it in ICCRG, despite the fact that we were trying to have it here 6 months ago. Jitan, you're up.
I just thank for the work. It's really interesting. I think categorizing QBIC as a MIMD may be not very precise, because QBIC actually runs this sort of TCP friendly mode. It would be good to know that how often the QBIC internet connections are actually in this region, because in that mode, it's really just running Reno. So
So I think that's a really interesting point, and I think that's a little short-sighted on my my half. So QBIC, I agree that QBIC can actually be both MIMD and AIMD, but as far as actually measuring how often it does this on the internet, I don't think it will be possible to do this with our current tool, since we essentially isolate the flow we are measuring in the localized bottleneck. So it's really not competing with other flows.
Thank you, Yucheng. Praveen, you're next.
Ayush, great work. Thanks for presenting this. One question I had was any early thoughts on being able to distinguish BBR and BBR v2?
Okay, so we did actually plot out graphs for BBR and BBR v2 as well. They have very distinct congestion window responses, but the problem we are having right now is that BBR v2's congestion window response is not consistent. So given BBR and BBR v2, we can distinguish between them, but given BBR v2 and some noisy measurement on the internet, we're not able to pick whether it's BBR v2 or not. So we need to do a significant amount of work in that direction to be able to make this distinction.
Thank you, Praveen. Jonathan, you're next.
Thank you. Are you planning to incorporate ECN response characteristics into your research?
That's actually an interesting idea, but we have not done this so far. But that's definitely a direction we would like to look into. So, I mean, not only just ECN, but possibly later on being able to classify quick connections as well. So those are the two key directions that we have not specifically looked into so far, but we definitely would like to look into in the future.
All right, thank you.
Well, thank you everyone for your questions, and thank you, Ayush, again for presenting this. Ayush, I'm assuming that you're going to be subscribed to the ICCRG mailing list?
Yes, yes.
Okay, excellent. So if you have questions, take it to the list, please. Ayush will be there on the list, and you can also give him more suggestions for what he could do to continue this work, because I think this is very useful work, and its use is also in being able to find out how the internet is changing as time goes. So thank you again.
Yeah. Thank you.
Moving on, we have Neil. Neil, to defend why BBRV2 might not actually be noise, as Ayush was suggesting. But I'll leave that for you to do, Neil. Take it away. Oh, actually, let me get you your slides first. There we go. All right, take it away, sir.
All right, great. Thanks, Jana. So I'd like to give a quick update on some BBR work at Google. This is joint work with my colleagues at Google listed there, including folks on the TCP team, Quick team, and the Swift team. Next slide, please. So in brief, some aspects that I'd like to cover include a main focus on some work that we're calling BBR Swift, where we're looking at using delay as a congestion signal inside data centers. And then briefly, I'd like to touch on a second topic about scalable loss recovery handling and some of the considerations that we think are kind of interesting as we've looked at our experiences with BBR and PRR and the question of how scalable are these various styles of multiplicative decrease when there are large decreases in the available bandwidth. And then I'll do a quick summary of the status of BBR at Google and a quick wrap up. And just to sort of set the context here about what we're trying to aim for this talk, we mainly wanted to share our experience with some of these experiments and algorithms we're trying out. And we wanted to invite the community to share any feedback you have. And of course, always encourage you to share any test results or issues you see or patches, traces, or ideas generally. Next slide, please. So the first part of this talk will be about what we're calling BBR Swift, where we're using delay as a congestion signal in the data center. Next slide, please. So a little background here for folks who haven't run into it. The Swift congestion control algorithm is one that some of our colleagues at Google recently published at SIGCOMM in 2020. And at a high level, one of the interesting aspects of the algorithm is that it uses the network RTT and host delays as the primary congestion signals, although it also uses loss. It generally tends to try to keep the queues low enough that loss is quite rare, and so the delays are very much the primary signals. And of course, this crowd will notice right away that this use of network RTT means that there are particular scopes where this is an appropriate and feasible algorithm. And in particular, this is appropriate where you have traffic that's inside a network with a known topology or a known RTT properties, which applies to a lot of today's data centers, which have very regular topologies where the operators know the expected RTTs. Another requirement here for scopes where this makes sense is that the network interface cards support hardware timestamps, at least receive timestamps. Transmit timestamps can also be useful. And then a third requirement is that all the traffic sharing the bottlenecks be Swift compatible, because the algorithm sort of requires that to behave well. And in terms of that algorithm, I think the two main points that are interesting about Swift are that it's using a fairly typical AIMD, that is additive increase and multiplicative decrease approach, where one of the interesting aspects here is that the multiplicative decrease is proportional to the excess delay, and we'll talk about the details there in a little bit. And then a second really interesting aspect of the algorithm is that when the congestion window is below 1, and it does support fractional congestion window values, it accomplishes that by using pacing so that the average number of packets in the network is fractional, and that allows it to handle large-scale multiplexing, that is lots of flows sharing a single bottleneck, which some people call incast, where you may have hundreds, thousands, or even tens of thousands of flows sharing a path that may have a BDP that can only hold 100 packets or 200 packets, something like that. So in terms of where Swift has been used so far, it has been used in production inside Google data centers by a user space and networking stack called Snap in the SOSP publication about that system in SOSP 2019. And this is used for a significant amount of traffic within Google data centers, where this is an appropriate environment since A, we know the target network RTT we're aiming for, and B, we know that all the other traffic sharing the queue and then is Swift compatible. And in this case, we use per quality of service queues to accomplish that segregation of different algorithms into different queues. Next slide, please. So so why would we want to use delay as a congestion signal? There are a couple of different advantages. So the first sort of class of advantages is that it provides a richer source of information about how much queuing is at the bottleneck. And this is quite interesting because it actually allows you to get a quantitative notion of the current degree or magnitude of queuing, which is something that you can't really get from ECN or loss signals. And this is useful because this allows you to react more quickly in cases where there is a long queue, to get rid of that queue more quickly and dissipate that congestion more quickly. But also, correspondingly, it allows you to avoid overreaction and potential underutilization if the queue is actually short. And you can think about that ambiguity if you consider, for example, a DC-TCP style shallow threshold ECN signal, where you might have a sustained ECN signal that lasts for quite a while, and the an EWMA filter of that might turn that into a very high alpha, for example. But it's still quite possible that that Q, even though it has lasted a long time, is quite shallow, and so it's quite easy for an algorithm to sort of overreact to that, whereas a delay signal allows you to avoid that issue. So the second class of advantage for a delay as a signal is that it gives you sort of a known target latency for engineering your systems, and this applies to several different pieces of the puzzle here. One, it helps applications to sort of predict the latency that they should expect. And second, it allows people who are engineering the network itself to set SLOs or service level objectives, and that can in turn help inform monitoring and alerting, because you sort of know what to expect or what you're aiming to achieve at least. By contrast, using loss rates or ECN and monitoring those and conveying those to applications, it makes things actually quite difficult to translate into application performance. So if you tell someone to expect a 0.1% loss rate, what are applications supposed to do with that? They don't really know how to translate that into latency expectations, and it's a tricky thing to do. And finally, at a high level, a key piece of the puzzle here is that to make this work, we need accurate delay measurements for network and host delays. So next we'll talk about that. Next slide, please. So BBR Swift, the primary signal that it's using is we call network RTT, and that's something that the data center computes by basically computing the total round trip time for a data segment minus the receiver ACK delay. And so we've drawn a diagram here to sort of illustrate that, and we've shown the total RTT in this sort of teal color and the receiver ACK delay in this sort of orange color. And then the network RTT component you can sort of visualize as the purple path of the packet there, and the sort of vertical distance of that represents the network RTT. So we can consider a specific example depicted here. If we look at the sender here, the data sender, TCP-A, it schedules some packets, or schedules a packet to be released at a particular time from the pacing layer. That packet travels across the network as data P1. It's received at the receiver here, at the receiving NIC, but then there are all sorts of interesting delays that can happen on the receiver side for various reasons. So one big delay source that we've noticed is power saving C states. So often servers that are not running at 100% CPU utilization on all the CPUs will take the opportunity to go into a power saving state. And if the packet arrives and the NIC that's handling the receive interrupt is actually in a power saving state, it can take quite a bit of time to wake up. Sometimes, often, that's longer than the actual RTT of the data packet, so that delay is significant and needs to be quantified. Other delays happen because the TCP stack might be processing a whole queue of packets, not just one packet. And then, of course, in TCP and other protocols, there's often an intentional delayed ACK mechanism that comes into play as the receiver is trying to piggyback that ACK on hopefully some outgoing data segment later on. And so if you think about all of these delays, you could have various combinations. And in this protocol, what happens is the receiver is able to convey that receiver ACK delay back to the sender. And to do that, we use basically a new timestamp option that we've described earlier in the week in the linked internet draft here, that we are calling extensible timestamps, or ETS. So you can check out the TCPM slides and presentation, and also the linked internet draft that describes the details. But basically, we'll talk about some of it. And an interesting thing to note here in the diagram is that the data and ACK transmission times are measured by TCP, and here in this picture, the data and ACK reception times are measured by the NIC and conveyed via the NIC hardware receive timestamp mechanism to the TCP stack. Next slide, please. So how is this signal used in the algorithm? So in BBR Swift, this is an extension of BBR v2, where the core aspects of BBR v2 are unchanged. And in particular, if a connection does not have the delay as available as a signal, it is going to behave exactly as the algorithm that we've documented at the IETF and open source with respect to its response to ECN, loss, bandwidth, min-RTT, and so forth. But what we have here is an extension to BBR-v2 that's based on the Swift algorithm. And a key piece of this is basically a new configuration parameter, which is the target RTT, the RTT value that the algorithm is trying to seek in some sense, and trying to maintain RTT values near that target. And inside of a data center, you can think of this as being in the ballpark of, or in the order of 100 microseconds. Although, you know, a particular installation would get to choose the target that makes sense for that installation. And then how is that target used? Basically, the algorithm at its core says that if the network RTT that's been measured is greater than the target, then we do a multiplicative decrease, where the multiplicative decrease factor is essentially proportional to that excess delay. And here the excess delay is quantified as network RTT minus the target RTT, and that's turned into a fraction by dividing that by the network RTT. So you can think of this intuitively as saying, what is the fraction of the delay that we're seeing that is excess delay, because we want to reduce the congestion window by a corresponding amount, so that we've cut out the excess fraction of the congestion window, which is proportional to the excess fraction of the delay in most cases. And then you can see here there's also a bound so that we don't reduce the congestion window by more than 50% per round trip. And again, this response happens at most once per round trip, as you would expect, since the sender needs to react and then wait a round trip time to see the impact of its reaction and see if it needs to cut further. So that's the basic approach that the algorithm takes. And one thing that is important to note here is that when this target RTT response is used, we disable the ECN response. So that essentially this target RTT response is used as a replacement for ECN if the administrator wants to use that in their site. And one interesting issue that we are still working on nailing down the details of is the question of how exactly WAN flows using ECN as a signal should interact with BBR Swift flows using delay as a signal. And there's an interesting set of issues there. And we have some ideas that we're exploring. One kind of approach would be to say that WAN flows can dynamically set the target RTT based on where they see the network RTT around the boundary between ECN marked packets and non-ECN marked packets, which gives you a sort of sense of the target RTT that you'd like, where the ECN mechanism thinks the delay is at a good level. Next slide, please. Jenna, how am I doing on time? Yeah.
Not well. So that's what I wanted to point out. We have 7 minutes left and a lot of slides. So
great.
You want to, decide how you want to do this.
Sounds great. Yeah, I'll adjust. Thanks. So just a quick sketch of the kinds of results we see with this class of algorithm. So here we have a sort of very simple or basic incast scenario with two machines, each machine is sending 1,000 bulk TCP flows, so 2,000 flows in total. And we're comparing DC TCP, BBR v2 with ECN, and BBR Swift. The thing to notice here is that because of the large number of flows and DC TCP is sort of operating C-WIN bound and act clocked, it is basically trying to maintain at least one packet in flight for each flow, which leads to a very large standing queue of all of those excess packets, which leads to a large loss rate that you can see here, 6% for one machine, 66% for the other machine. and it also has some sort of fairness issues. Whereas BBRv2 with ECN does a little better. It's a little bit more fair. The retransmit rate is considerably lower, around 1.6, 1.7%, and the fairness is a little better, or actually comparable, I guess, to DC TCP. And then if we look at BBR Swift, you can see that the algorithm, because it's able to use the pacing rate to match its sending to the aggregate delivery rate, it's able to keep that queue nice and small, correspondingly achieve a very low loss rate. Here the loss rate is about 0.05%. And you can see there that the network RTT on average is around 93 microseconds, corresponding to the 50 microsecond target that was used in this particular experiment. And you can see the Jane's fairness index is fairly good. So that's just a quick comparison to give you a sense of the properties. Next slide, please. So where are we? We're preparing for production testing. We're basically rolling this out in preparation for doing large-scale production workload testing. And we're also planning to release this code as open source and document the algorithm. And this includes the timestamp implementation as well. And basically the goal here is we want transports to be able to use this algorithm as their CC on connections where a target network RTT can be known. And we know that the coexisting traffic is also running a compatible algorithm. And we'd also, in the long run, like this to be usable on both physical machines and inside virtual machine guests. Next slide, please. So the second part I just wanted to briefly mention was some interesting observations and issues we've seen around congestion control and loss recovery. Next slide, please. So perhaps the slide title here is a little provocative, but I thought it was interesting to sort of raise this issue that we've seen because our experience is showing that both on data center traffic and on the public internet, this is an interesting issue. So as this audience well knows, traditional TCP congestion control uses a multiplicative decrease upon round trips that have packet loss. Reno will cut to 0.5 of the old congestion window. Cubic will cut to 0.7 per round trip. But an interesting question arises, what if the bandwidth available to a flow suddenly drops by a very large amount, say 100x, 1000x. It sounds like a lot, but this can actually happen in the data center when you are partitioning work among thousands of servers, or even in the public internet when you drop from a well-provisioned flow going at hundreds of megabits down to a policed flow at a much lower rate due to an ISP policer policy, and where policers are quite well deployed quite frequently. So in theory, what happens in these kind of scenarios is that with something like Reno, you expect a number of round trips of very high packet loss until the flow reacts fully and adapts to the new congestion window. And in particular, you expect a number of round trips that is basically the old bandwidth divided by the new bandwidth, and then you take the log base 2 of that ratio, and that tells you how long you expect to see these high losses. So if there's a 1000x cut in the fair share bandwidth, you can see 10 rounds of high loss. That's the theory. In reality, it's actually a little bit different. With traditional TCP loss recovery before rack, it actually couldn't handle consecutive rounds of loss. And what tends to happen instead is you get a retransmission timeout, you cut your congestion window to 1, and you slow start back up. With TCP rack, but no proportional rate reduction, you actually see a reality that matches the theory, multiple rounds of high loss, and this can be quite painful. And we've definitely seen this in experiments where you use rack but no PRR. In the public internet, when you run into a policer, it can get quite ugly. But finally, if you're using rack and PRR, you get a nice kind of behavior where the sending rate is bounded to be quite near the delivery rate, and thus this keeps the loss rate at sort of a reasonable level while still robustly probing for bandwidth. And this is what you get if you say run a default Linux stack. You're going to get cubic plus PRR, and you'll get that kind of behavior today. Next slide, please.
You have 2 minutes at most.
Okay.
I don't think you to go through the 10 slides.
Yeah. Yeah. I just want to zoom through a couple of these. Yeah.
Sure.
So can we just So what we've done with BBR is for BBR v1 there was a sort of PRR inspired approach. For v2 we tried to simplify things by removing that and just doing a pure multiplicative decrease. But what we're seeing in our experience as we roll this out is that actually there are important scenarios where that does give you that sort of theoretical behavior that's quite poor. And so what we're doing is we're now trying in production various PRR-inspired responses, and we hope to update you in the future either on the list or in presentations with the results. Next slide, please. So wrapping up, next slide. So as folks know, we've open sourced BBR v2 and talked about it at previous IETFs. You can find the links in the slides here. Next slide. And just a quick status update. So for YouTube and Google.com public internet traffic, we've deployed BBR v2 for a small percentage of users as an ongoing experiment as we refine the algorithm and the code. We see reduced queuing delays and reduced losses versus BBR v1, getting closer to cubic levels. For Google internal traffic, we're deploying BBR v2 as the default, and we're in transition there. Currently, it is used as the congestion control for most of the internal traffic within Google. This is using the algorithm as previously described with bandwidth, min-RTT, ECN, and loss as signals. As I mentioned before, we're still in the process of rolling out the code for this network RTT signal inspired by Swift. Next slide. And in conclusion, we are actively working on BBR v2 and this variant we're calling BBR Swift, continuing to iterate, and we are open. We love to hear feedback on these approaches, test results, and so forth. And we definitely appreciate the survey results from the previous presentation, for example. So thank you very much, and hopefully we have a few moments for Q&A. If not, we can take questions on the mailing list.
Whitney's in queue, so I'll let her get in, but we'll have to take more questions offline. Go ahead, Whitney.
I'm trying to use headset. Is it better?
Yes, much better.
Thank you. Just a very quick question. So the network RTT is obviously used for BBR Swift. Is it used, like, how is the delay thing working in BBR v2 if network RTT is used or if it's not used?
Sorry, can you repeat that last part? How is the what used?
So are you doing the multiplicative decrease for BBR v2 as well in the WAN using network RTT or something else?
So in the WAN case, we are not using the network RTT signal. The basic practical issue there is that usually for WAN paths, you don't know the target round trip time ahead of time. And so in our deployment so far, we're definitely just using the target RTT within a data center. For the WAN flows, they're just using ECN and loss signals. We do have ideas about how we might unify those and use a delay-based signal. I guess I briefly alluded to that in terms of perhaps using ECN signals to find the target delay at which we'd like to match based on the transition between RTTs above that point where we see ECN marks, RTTs below that point where we see no ECN marks, and use that as a sort of way to find a target RTT dynamically for WAN flows, but that's a future work.
Right, but queuing delay can be measured, right? By just having a base delay and a target whatever delay, just like what Ledbat does.
Sure, but to have that base delay, you sort of need to, in general, to be able to distinguish a standing queue from a longer wire. It's it's can be quite tricky unless you either have knowledge ahead of time or you have an ECN signal or something that allows you to disambiguate those.
All right. Well, thank you so much, Neil, and thank you, Vidhi, for that question. Please continue this conversation on the mailing list again. I'm sure a lot of people are interested in the relationship between BBR Swift and Ledbat++ and questions on BBR v2. Please continue that on the mailing list. Thanks, Neil. Sylvester, you're up with your, I'm going to bring your presentation up. And there we are. Take it away.
Can I share my screen, or is that not?
Yes. Let me give you the screen.
I'm in the screen sharing queue, so it should be working.
I see. Yep.
Okay. Can you see it and can you hear me well? Can you hear me?
Yes.
Okay, and can you also see my screen?
Yes.
Okay, thank you. So, hello everyone, I'm Sylvester Nádas, and with my co-authors, we are interested in internet resource sharing. So, we run some testbed studies on fairness, and we chose BBR-V2 congestion control as a new level of congestion control to compare to existing ones because it's designed to be friendly to cubic flows as opposed to V1. It has scalable ECN response, and it already has some deployments. So we used 3 machines connected in a chain topology in our testbed, a traffic generator, receiver, and the bottleneck in the middle. And on the sender and receiver, we installed the BBR-V2 alpha kernel, and we used default Linux settings. We implemented several AQMs in DPDK, tail drop pi, GSP, step, pi square, dual pi square, and virtual dual Q core stateless AQM. We use net delay for RTT emulation of acknowledgements to emulate RTT. The bottleneck rates was changed between 100 meg and 10 gigs, and the results I present are with 1 gigabit per second. And we use several congestion controls, cubic, BBR-V2 in both scalable and classic mode, and DC TCP. We changed the number of flows from 2 to 100 in these measurements. So this is an example measurement results. We have 2 connection classes. Connection classes are identified by congestion control and RTT. So this was cubic 10 millisecond and BBR 10 millisecond RTTs over a 1 gigabit per second bottleneck. We changed the number of connections. Half is from one connection class, the other half is from the other. The buffer size is set as a factor of the RTT. So 0.5 means 5 millisecond in this case buffer. And we plot the relative goodput, where 1 is the ideal and the relative goodput of a connection class is the average goodput within the connection class divided by the ideal per connection fair share. And we also studied several AQMs. So we have seen reasonable fairness with tail drop when it comes to sharing between cubic and BBR-V2. It was much worse for small buffers. And we also have seen good fairness with CSAQM for basically all cases. So what happens with the different AQMs? We plotted the tail drop results as a gray shadow for reference. So with pi, the fairness is very similar to tail drop. While with GSP, we have seen huge degradation compared to tail drop for a smaller number of users. And it was similar to tail drop for a larger number of users. So what is CSAQM? Mentioned is a result. So in addition to existing AQMs, we also evaluate CSAQM, which is a core stateless resource sharing framework. It can apply a wide variety of policies, not only fair sharing, and it can enforce these policies for heterogeneous traffic mixes. And it also scales well with a very large number of flows because the algorithm itself is stateless. And it's also congestion control independent. It puts no assumption on how the congestion control behaves. It relies on packet marks with different values. Larger values mean more important packets. In congestion situations, packets with smaller values can be dropped or marked with a congestion experience DCM flag. And the bottleneck behavior is purely based on the packet values, so we don't have to do any flow identification. We don't have to use separate queues or decode the policy information in any way. Therefore, the implementation can be very simple and fast. At the same time, it needs some standardization, or it has to be done within an administrative domain because it needs a header field. Even though the AQM is almost like the existing tools that we were able to implement it in P4, you can find much more about it at our homepage. So getting back to results, we also used DCTCP-like congestion control. So we compare the fairness of DCTCP and BBRv2 in scalable mode. In this case, instead of changing the buffer size, we changed the target delay as a factor of RTT. And our key findings here is that while the step AQM prefers DCTCP, pi square AQM, for pi square, the BBRP V2 is the winner. And it's actually hard to choose which one is better. For pi square, the fairness is improving as the number of flows grows. By which step it gets worse for larger number of flows. And the CSAQM, as mentioned before, it provides a reasonable fairness in all these cases. Again, this was the relative throughput I have also shown for the BBRv2 versus cubic cases. So let's see how these AQMs are marking the connection classes. The ECN marking ratio here shows what is the fraction of the congestion experienced marked packets compared to the total number of packets. It's a logarithmic scale on the y-axis. It is clear that step and pi square, both connection classes are marked the same. And because the two congestion controls use the ECN feedback differently, this results in bad fairness as shown in the previous figure. And with CSAQM, there are seemingly no connection with the marking ratios of the connection classes, so there is no clear formula how to mark the packets. But this is exactly the right marking ratio to achieve good fairness. We also compare the fairness between BBRv2 scalable and cubic flows over dual pi square bottleneck. In this time, I present time series plot, and the number of flows from the different classes changes between 0 and 50. You can see the number of flows at the top. And you can see that dual pi square can control BBRv2 alpha traffic class, leading to significant unfairness between the two traffic classes. In general, when the number of BBR2 flows is large, the classic flows experience very small throughput. So please be aware that this is a logarithmic scale. You can see the total class throughput at the top. And we believe that this is because BBRv2 applies a model-based congestion control. But what happens if the network works with different model? So this kind of unfairness can happen then. And comparing that to dual Q core stateless AQM, that can provide a pretty good fairness by not assuming anything about the congestion control used. So in summary, we have performed much more testbed discernments. I will have a link to all the results. But most congestion controls have RTT fairness issues, even in mono congestion control scenarios. And evolved congestion controls have fairness issues with legacy. BBRv2 versus cubic fairness is very dependent on settings. I actually shown some good results. Sometimes it can become quite bad. And DCTCP versus BBRv2 scalable mode in general provides bad fairness. And then an interesting finding we have seen is that AQM tunes for a specific congestion control have actually the potential to hurt the resistance even more, and they very rarely help it, even though they help in, for example, multi-RTT scenarios when the specific congestion control is used. So there are examples for the graded performance compared to teardrop or span, and it's pi and GSP for BBRv2 versus cubic, pi square for DCTCP versus BBRv2, and dual pi square for BBRv2 scalable mode versus cubic. So in summary, the congestion control evolution has accelerated. It's also possible to do user space congestion control or congestion control in BPF. But it's very hard for a new congestion control to be both innovative and to be fair to existing congestion control. So we don't want to say in any way that BBRv2 is a bad congestion control. We believe it's actually a quite good one. But as also stated in reference number 1, TCP friendliness greatly constrains how we can handle congestion in the internet. And why fairness to existing congestion controls is often demonstrated in special cases, that is not universal. And as the number of deployed congestion controls increases, this becomes even harder. And even the harm-based bar for a new congestion control is close to impossible to meet. So this is, I refer to the presentation which Jana mentioned at the beginning. And I believe that 2 congestion controls can be still tuned to be compatible for some scenarios, but we are skeptical that this can be generic enough or this can be done among several new congestion controls. So what can be done? How can we provide fairness? What are the ways forward? So today, fairness is dominated by end-to-end congestion control and over-provisioning, and we question whether this is still the way or whether actually TCP friendliness to Reno and or data center TCP a point of ossification, and the similar point of ossification is AQMs tuned for a specific congestion control behavior. There is other method used quite often, that is fairness scheduling by scheduling the network, for example, FQAQMs and hierarchical QoS. And this is working quite well. It has its issues. It's not practical for high-speed users. It results on equal or static sharing, which is not always optimal. And communicating policies to every potential bottleneck is hard. So we believe that cooperative approaches like CSAQM has a good potential for controlling resource sharing. Flow identification and policy decisions are done at the endpoint or at the network edge. In this case, the implementation in the routers is then very simple and invariant to the number of flows or invariant to the policies used, though it requires a header field. But to be on the fair side, headers or some kind of solutions are needed for many other solutions, like we have ECN, we have an L4S bit, or we are proposing an L4S bit, and also there is DSCP. But this one requires a new header field. So to compare these solutions, created a table with the 3 methods: end-to-end congestion control, in-network, and cooperative sharing. So end-to-end congestion control provides fairness by congestion control, but it has fairness issues, and the RTT unfairness is hard to solve. In-network scheduling provides very good fairness and actually solves RTT unfairness, while cooperative resource sharing provides fairness by packet marking plus AQM. It provides good fairness, and it also solves the RTT and unfairness issues. So resource sharing is dynamic for end-to-end congestion control and cooperative, and pretty static for the in-network solutions. And the end-host control, the end-to-end congestion controls has a full illusion of the end-host control. And I'm saying illusion here because there is still a fate sharing of packets, and also congestion control aggressiveness and RTT is very chaotic and actually hard to control. There is limited control of end-hosts in the in-network scheduling scenarios, and with the cooperative, if actually the marking is done at the endpoint, there can be high amount of control, while it can be limited if there is edge marking. So it's if the end-host is not communicating with the edge. And congestion control evolution is constrained by end-to-end congestion control based fairness because of the harm to existing congestion control, and it's less constrained in the 2 other cases. And the bottleneck complexity is low for end-to-end congestion control. This is basically the bottlenecks we have today. We don't have to change anything. For the in-network, we believe that in most cases, some kind of CPU-based solution is needed, especially for high number of flows, or especially if you want to control hierarchies of resource sharing. While it's medium for cooperative, we were able to successfully implement the AQM in P4. There is no need for signaling for end-to-end congestion control. there is a high need of signaling for every potential bottleneck in the in-network case. And depending on how we do marking, some kind of signaling might be needed. And actually, the packet marking is a kind of in-band signaling also. Also, the end-to-end congestion control is the current state of affairs, so it doesn't require standardization. The in-network likely requires some signaling unless we are okay with the per flow fairness, basically. And the cooperatives requires some kind of standardization for packet marking. So questions to community future work. First question is what more to include in these type of evaluation, congestion controls, AQMs, RTTs. Also, what are the typical implementations when it comes to operating systems and meaningful defaults of the congestion controls? Also, very important question to discuss and is that what are the typical bottlenecks? What is the speed of them? How many flows do we have over them? And how many bottlenecks shall we consider in the path? And the third interesting question is the effect of the sub-millisecond internet on fairness. So some caches are very close to the edge. And do non-CDN flows still have a chance when sharing a bottleneck with these sub-millisecond flows? So you can find our results at these web pages. And I'm looking forward to your questions and comments. Thank you.
Sylvester. Koen is in line. Go for it, Koen.
Hi, Koen here. Can you hear me?
Yes.
Yes.
Okay. Thank you for this work. It's very interesting, and I think it opens also a very interesting discussion. Because indeed, from L4S point of view, the strategy here is to try to line up long-term congestion controls to be fair, so that the AQM, like you showed, doesn't need to make differentiation between the different types of congestion controls. Well, for L4S, we did a big hub between the classic and L4S traffic. So I think it's very valuable to do these comparisons, definitely. It's also a good discussion whether we should do this differentiation or not. From within the network, and whether the network is really responsible for doing this, or that we also should focus also on the cases where it's not possible to do something in the network, to also make sure that congestion controls really have a common protocol and a common behavior related to ECN marking. Definitely drops, but also I think it's more important to have this behavior on a longer term. Yeah, I think it's a good point for discussion. And as you know, L4S is relying on the end systems to do at least their best they can do to line up. Mm-hmm. I don't know. Yeah, I guess it's up to other people also to have this discussion. But thank you for the work. It's very useful.
Thank you for your comment, Koen.
Thank you, Koen. And thank you so much, Sylvester.
Thank you.
I would again encourage the conversation to continue on the mailing list. This is for the presenters as well as for the other folks in the group. Please go ahead and kickstart conversations on the mailing list. I think that's a much higher. You can have much deeper and higher bandwidth engagement there. All right. Moving along, is Bob or Koen, which one of you is going to do this?
I'm probably going to start, and then Koen will do. We'll switch to Koen in the middle.
Okay. Just a quick note, Bob, that we have 16 minutes before the end of the session.
Yep.
So I want to give you a heads up on that. Okay, take it away.
All righto. So this is I'll talk about TCP Prague, which the authors are there. Let's move straight on. Next slide. Jana. Yep. So as I mentioned in TSVWG, if you were there, this is going to be a bit of an invitation to collaborate, because when we first started on L4S back 5 years ago, I think, DCTCP that we were using, version 3.19, the Linux kernel, just happened to work really well. But and we carried on using it for maybe 3 years, because we were really focusing on AQM products. We were mainly network companies. We were dealing with the some safety aspects, but we were largely just sticking with what worked. And when we tried to use later versions of the kernel, it didn't work that well, but we were mostly just sticking with what we've got. And then we started getting criticisms that didn't work with later kernels, and finally started looking at it and found there was a real rat's nest of tangled bugs, and they seem to have come into the Linux kernel since 3.19, and it's taken us, it took us months to work it all out. Anyway, so Koen's going to talk a bit about that in the middle of this talk. I mean, we fixed it probably about a year ago now, but we haven't really talked about it since. So what we really think is that it got a bit of a bad reputation for not being possible to reproduce any of our results, because no one could use it on the latest kernel. And so we want to do a bit of a relaunch now that the code base is usable for others. You know, it's been up against the latest version of the kernel now for a good year or so, and so and also it seems likely that we're going to start seeing deployments in the network, probably not like in the next few months, because they've got to depend on the code point assignment. But once that does come, I think you'll start to see it in production networks. So I'll come back to the invitation to collaborate at the end, if we can move on to the next slide. That was just a bit of background as to why we're giving this talk. Jenna, next. So first I wanted to give a very, very quick tutorial on DCTCP. So for those who aren't familiar with some of the things Koen's going to talk about, it will give some context. Next. Right, so I guess the main thing I believe is important about data center TCP, and it's not often seen this way, is that the smoothing of the congestion signals shifts out of the network, where AQMs traditionally have filtered out variations in the queue. Obviously the queue still varies. They've filtered out measurements of variations in the queue before signaling drop, because they didn't want to signal drop too early. And because DCTCP uses ECN, it can shift that responsibility to the end system. And then the important difference is that when it's in the network, the delay that the smoothing has to add, just in case it's not really, just in case the queue variation is going to go away, has to be about a worst case RTT, typically 100 milliseconds. Whereas once you move to the end system, it can smooth based on its own round trip time, and all the end systems that are using a particular bottleneck can all be smoothing on their own round trip times. And also, very importantly, the zero there, that they actually get the signal with no smoothing delay if they want to react to it straight away. So if you can do next slide, it builds, Jenna, then they can choose not to smooth at all, for instance, during flow, when the flow is starting up. And of course, you've got zero delay on the network side as well. You've got an instantaneous queue, AQM, sorry. So next, I said I'd go quick, and I'm not, am I, through this. So the way that the end system smooths in DCTCP, this is really the only difference from Reno, other than a load of implementation details that are different, but it's the only real design difference. And it just takes a fraction of the marks every round trip time, does an EWMA of it, and then uses that EWMA to scale down the reduction, which is why it does a reduction by extent. Next. Yep. So the effect of that is the memory in the end systems. It deals with the fact that short flows and bursts are effectively unresponsive, and what it does, in the classic approach, not what it does yet. In the classic approach, and including BBR, short flows burst into the buffer. So the buffer is held slightly full, even with BBR, and fuller with obviously tail drop and the rest of it. And then short flows burst into the buffer. Whereas with data center TCP and L4S and so on, the long-running flows leave headroom for the recent level of short flows, and they've learned that headroom from maintaining that EWMA of the feedback, and so the short flows burst into that headroom and stay below the threshold, unless they're just occasional surprise short flows that the memory isn't used to. Next. So that's really next, Jenna. So this is now the core of the presentation. Next, please, Jenna. And just wanted to start with a traffic light slide that I've used before many times, but you'll see it's got some extra bits added on the end. These are all the bits of Prague congestion control that have to be there to be safe on the internet for in the first block, the requirements, and to perform well, which is the second block. And that used to just have 2 items in it, the top 2 in the performance area. But we've added a number of others as we've found all these problems that Koen's going to talk more about some of those areas. And I'm not going to even read out all the titles, and you can have a look at this slide in your own time, because the point of it is merely to show that there's more stuff added on the bottom, including bug fixes, which are obviously performance improvements. And when I say bug fixes, these aren't sort of code bugs, they're performance bugs, where the effect of the bug is to reduce the performance. So Koen, I don't know whether you want to pick up on this slide or move straight to the next one.
Yeah, next slide, I guess, for the time. So first slide I want to show is the improvements we did in Prague. We had to do in Prague to solve the quite bad degraded behavior of data center TCP in the recent kernels. So if you look, the queuing latency spikes very high. And we found out it's mainly due to less responsiveness on one hand because of rounding downs, also not enough number of bits which were used in integers. We definitely had issues with TSO sizing and the pacing with it, so the default settings which we had to adapt. There are bugs in PRR which have a small impact on cubic and other, let's say, classic congestion control, but had a huge impact on data center TCP. And also to even further improve smoothing, we also found that there was a need for partial additive increase. So instead of, and there is a slide for it, non-response at a certain time, which makes it also vary a lot. So if you really look at it, under the same conditions with the 1 millisecond thresholds, if people tried in last year to reproduce, and I also saw that the presentations from Sylvester also use data center TCP, the latest kernel version, you will see it really underutilizes the link. So in our Prague version, we fixed all those, and it was really difficult because we had to remove all of them before we got the good result again. So we spent quite some time, a few years or a year ago, or more than a year ago in the meantime, so to get back our initial 3.19 results. So I think that's very important to know. If you want to do experiments, please use Prague instead of data center TCP in the latest kernel. Next slide. So yeah, the smoother steady state additive increase, if you are aware, if data center TCP is driven by an AQM, which is smoothing, like in a coupling or in a pi square or whatever other AQM, you expect that every round trip time there are marks. But classic congestion controls and also data center TCP took it over. It suppresses the additive increase in the round trip time after a multiple decrease, so when it's in the congestion window reduced state. So that means that if you get marks every round trip time, or you expect that you don't have any opportunity to increase. So because of that, your AQM will start to oscillate the interaction because it's putting the right marking probability, and then it becomes non-responsive. So it goes down because it allows it to increase again, and then suddenly it's the probability is too low. So all of these interactions were creating extra periods of going up, going down, which are not good, of course. And then also for round trip time dependence, if you have a very big round trip time, of course, if you compete with a small round trip time, you will definitely get every round trip time marks. So that means that a bigger round trip time will get pushed down completely. So this is an important difference between Prague and data center TCP that we have in Prague. So in Prague, what we do, we increase on every ACK except on the ones that echo an ECN mark. So it's a kind of proportional additive increase as well. So we do only a half a packet increase if 50% of the packets are marked in that case. Okay, next slide. So to compare a little bit, what are the real benefits of using Prague or L4S or the data center TCP kind of flows is that obviously we have a very smooth throughput and a very low latency. You see here in blue at the right, we are below 1 millisecond, still having full link utilization in a wide range of cases. Okay, there is a worse startup and it becomes worse when the BDP becomes bigger, so for longer round trip times. But these are things which we haven't fully focused on, or well, there is research in progress. Work is being done, but okay, it was a little bit shifted behind because of all the safety issues and the discussions on the mailing list. But anyway, there are potentials clearly potentials to optimize that. So comparing it to, okay, the best case, CODL 5 milliseconds on a bottleneck, there is still a significant improvement, let's say. Next slide. So one of the things we have also worked on is a better round trip time independence. And we can play with it and do whatever we want with it. So that's the main message. The discussion, and there is a lot of discussion on the mailing list about what it should do. But I mean, TCP Prague in itself can be made completely round trip time independent, like is shown at the right side. So here we have different flows from half a millisecond round trip time, 1 millisecond round trip time, 10 and 30 milliseconds. If you look at how it works on a CODL AQM, which has a buffer of 5 milliseconds, so luckily it adds 5 milliseconds to each round trip time, and if it's then proportional to the 1 over the effective round trip time, including the buffer, you will see the different rates. So the one with the 30 milliseconds really has a very low latency compared to the 0.5 and 1 millisecond, which effectively get around 5-6 millisecond latency. If you look at Prague, which only has 1 millisecond buffer, initially in the beginning of the flow, you get an impression of what would be the rates, and what we did in Prague is after 500 milliseconds we enable this conversions towards fair share. So you see after a while all the rates go and share the link evenly. And why do we not immediately do that? Because we think it would be a good strategy to start from a dynamics point of view to still get the benefits of your lower latency. But fairness and convergence is a process of longer time, so we only need to that over a longer time. So we don't want to disadvantage smaller round trip times when it's about dynamics, but we don't want to give disadvantages to the longer round trip times if it's a matter of downloads. And if the round trip time is very long, well, there is not much. If the base round trip time is already very long, there is not much possibility to do interactive applications, and the shorter term interactive mechanisms will not make a big difference. So that's a little bit the strategy that we follow. But that's of course also for discussion, or it can be adapted based on applications that use this mechanism. But the good point is that, and I think it can be done in every congestion control, that after a while, if you are in a very steady state, that you can all converge to the same fair throughput. For the rest, it's still a matter of being non-responsive and use whatever there is, because congestion control cannot happen in a very short time frame, especially not for short transactions. Anyway, so okay, next slide.
Koen,
Yeah.
Koen, we are past time. Do you want to wrap up in a minute?
Yes. Next slide, quickly. Okay, Bob.
Yeah, just I think that there's just two more slides actually, and I'll go very quickly because I've said a lot of this before. So we think there's a lot of potential in exploiting high fidelity ECN markings, particularly as there are signs that there are going to be operators deploying that. So network operators. So there's a list here of possible topics to work on. I was hoping we could go through this, but I guess it's a bit late. Just so you'll just have to quickly look at them. But there, if there's any people in the room that are looking for a research project, coming to the end of a master's, wanting to do a PhD or whatever, or PhD students looking a bit lost, or anyone who's a postdoc or whatever, there's all sorts of things there to look at. We're sort of wanting to try and be a bit more open and be a bit more helpful. And the next slide was really just we want to start thinking about a better way to be able to visualize comparisons, to be able to come up with common metrics, because at the moment a lot of the metrics aren't common. There are drafts on reference test cases and RFCs, but not many that really focus on low latency. 7928 is probably the closest, and possibly, well, certainly everyone's got to use reusable tools. I don't think common tools is an aspiration that is realistic, but certainly make sure that other people can use your tools. And so I think we're going to end there. Just if you can switch to the last slide and leave it up, that's just some pointers to how you get involved. Thanks. Any questions? I know we're over time, but.
Yep. Thank you so much, Bob and Koen. We have two people in line, and I'm going to cut off the line after that. Yicheng. Well, Gauri is in line too. So, Yicheng, go.
How do you solve or improve the RTT fairness by the proportional increase on the X? I can't quite get the insight there.
Koen, that sounds like it's for you.
Yeah. So your question is how did we improve it?
Yeah, how do you get better RTT fairness?
So what we do is that we adapt the additive increase. So we slow down the additive increase, and we.
Can I jump in, because I think I know Wang Yu Chung. The description of what Koen explained for the additive increase in this talk wasn't there's another change to the additive increase that he hasn't talked about in this talk for doing the RTT unfairness. Does that help?
Okay, I guess I'll get it offline.
Yeah.
Time's tight. Yeah.
Well, I did a presentation for it. I think in the previous or one of the previous ICCRGs. And if you have questions, maybe ask on the mailing list. We can go in more details, I guess. Right.
Sure. Thank you.
All right, Jonathan, you're up next, and let's keep this quick.
Okay, I'd just like to highlight the fundamental feature of TCP Prague, which is that it relies on a redefinition of the congestion experience mark in ECN. The standard definition is that it requests a multiplicative decrease, but Prague expects it to mean an additive decrease. So I think a lot of
it's multiplicative, Jonathan.
So I think a lot of the discussion is going to have to talk about the resolving that discrepancy.
I think
it's multiplicative.
Well, no, it even doesn't matter. I think it even doesn't matter, Bob. It's just in the long term, when we are in a kind of steady situation where we want fairness in download situations or whatever. If we really can measure what is the share of each flow, there we want to converge to or an abeyance, let's say, to a kind of marking probability to rate equation. And that's all of it. Yeah. It doesn't mean that you have to be AIMD. You can do whatever you want, very clever. And even if you see that you're in a dynamic situation, you can make optimal use of the dynamic situation. It's only, and it's the only way to measure if you are on a long-standing link, very greedy situation. It is important to converge because that's where it's measured. But on a short term, you can do whatever you want. Well, that's maybe another point of discussion. What are we going to allow? But in Alvarez, you still need to keep the latency low, for instance. But well, that's the main difference. And there is no obeyance.
I think you're being far too clever here. Jonathan's just got a misconception that because the reduction is equivalent to reducing by half a packet every mark, he thinks that's additive. But it's repetitive additive, therefore it's multiplicative. That's the whole point.
No, each mark is additive in Prague.
No, it's actually not in Prague. It is in Relentless, but in Prague it does a multiplicative decrease based on the number of marks over a round trip.
All right. With that, I will call this. This is thank you so much, Bob and Koen and Jonathan for asking the questions. But I'm sorry that we had to rush a little bit at the end. But thank you so much, and thank you everybody for staying 8 minutes past time. This has been an excellent session. Please continue the conversations on the mailing list. Let's use that medium. I think there are a lot of conversations that we want to have. So let's have them there. Enjoy the rest of the IETF, and hopefully we'll see you again soon.
Thank you, Jana, for chairing us so well.
Thank you.